Welcome back. All right, so we had just talked about plasma proteins, and the majority of these plasma proteins that we have actually are produced by the liver. The only, or one of the plasma proteins that is not produced by the liver is the antibodies. So immunoglobulins or antibodies are actually produced by your B and T lymphocytes. But the liver produces the majority of our plasma proteins, which means the liver is very important in helping us maintain colloid osmotic pressure because it's producing most of the proteins in our blood. So colloid osmotic pressure is the pressure exerted by those proteins to pull fluid back in. So hold on, if our colloid osmotic pressure is increased, more fluid is going to be pulled in. If colloid osmotic pressure decreases, then more fluid will remain in the interstitial regions. And so to remind you of what osmosis is, it's the movement of water from a higher to lower concentration down a concentration gradient. So here we have water in a tube with some membrane here. And on this side, we have very few solutes, but on this side, there's a lot of solutes. So water's going to move until they're at equilibrium with a water-solute ratio. The same thing happens in our blood. If we have more proteins in our blood, fluid will move into our blood. If we have less proteins, fluid is going to leave our blood. Make sense? So what happens when we have less protein? This would be known as hypoproteinemia, so low protein in our system. And this can be caused, or this can occur when you are being starved. So if you don't get enough food, you can actually have too little fluid, and the amount of fluid in your system is going, or I won't say the amount, the fluid that is in your blood is going to pool in those interstitial regions because it's not being pulled out like it's supposed to. And that causes this extreme edema that we see here. Here we see another form of edema called ascites, where fluid pools in the abdominal cavity. For the same reason, you don't have enough proteins to pull the fluid back in, but it's not because of a protein deficiency. In this case, the liver is not functioning, and since the liver produces the majority of our proteins, if we don't have a functioning liver, then the fluid isn't going to be pulled back into our system. And here is another disorder called Kwashiorkor syndrome. This is a disease that we see in children in developing countries because they do not get enough protein. In general, they have this large abdominal cavity. Fluid is pooling in that abdominal cavity because they don't have the protein to pull the fluid back. And the reason for this is they're not getting protein in their diet. They're mainly fed on carbohydrates, so cereals, grains. They need more protein. It's a very sad disorder. So now let's talk about formed elements and what they come from. So all formed elements come from the same stem cell. We have the stem cell that hasn't decided what it wants to be. So that's kind of what a stem cell is. It's like a student who is still kind of keeping their options open. I don't know where I want to go with my life yet. And the stem cell that does this is called the hemocytoblast. Once it picks a line that it wants to be, it's going to differentiate into either a lymphoid stem cell or a myeloid stem cell. And from there, it can then become, if it's a myeloid stem cell, an erythrocyte, a megakaryocyte that breaks down into platelets, a monocyte, a neutrophil, an eosinophil, or a basophil. If it wants to be on the lymphoid stem cell line, it can be a B or a T lymphocyte. It can be a natural killer cell. There are multiple types of B and T lymphocytes. Hemopoiesis is the production of blood, And all hemopoiesis occurs in red bone marrow. So we have multiple blood cells that are being produced on a daily basis. And all of it occurs in our red bone marrow. So in children, that's going to be found in the marrow cavity as well as in the spongy bone. In adults, it's in the spongy bone, mainly in our long bones and in our flat bones. Hemocytoblasts or hemopoietic stem cells are what differentiate into all of our different white blood cells or red blood cells. And I already talked about this. Myeloid hemopoiesis forms the majority of our blood cells. Lymphoid hemopoiesis forms all of our lymphoid or lymphatic lymphocytes. That's what I want to say. Erythropoiesis is a specific formation of blood, and it's the formation of red blood. And this makes up the majority of all of our blood cells. Remember, 44% of our blood is red blood cells. 1% makes up all the other cells in our blood. And then the 55% that's left over is our plasma. So for erythropoiesis to work, we need to have all the components. We need to have the amino acids. We need to have vitamin B. We need to have iron. And what happens is we have this myeloid stem cell that gets stimulated by an erythrocyte colony-forming unit that is going to convert into an erythroblast, which will then convert into a reticulocyte, and then to an erythrocyte. I don't care if you know this specific route. What I do care about is that you know that it's a myeloid stem cell, and once we have a mature erythrocyte, we have a cell that has no nucleus. You can see here in the erythroblast we have this large nucleus. We're producing tons of hemoglobin, but as the hemoglobin is taking over, the nucleus and all the organelles start to degenerate, and they're released, and so basically we just have a large sac of hemoglobin. This process takes about 3 or 4 days, depending, and it's stimulated by a hormone called erythropoietin that's produced in our kidneys. Red blood cells only live for about the max, it says average, but the max is about 120 days. So most red blood cells don't live that long. They live, some might live only for a few weeks. Some might live for, a month or two. And the reason they can't survive very long is because they have no nucleus. They have no organelles, and so they can't fix themselves when they are damaged. Leukopoiesis is the production of white blood cells. And leukopoiesis is a little bit more intense because we have to make all of our white blood cells, which includes our granulocytes, monocytes, and lymphocytes. All of our granulocytes, those are our phils. So eosinophils, basophils, neutrophils. Then our monocytes and our lymphocytes. Thrombopoiesis is the production of platelets. So it starts with a megakaryoblast that is produced from a myeloid stem cell, and that's going to form a megakaryocyte. It's a huge white blood cell that then dips in, so it kind of sticks processes or extensions of its plasma membrane into the blood from the bone marrow and breaks off little pieces at a time, and those little pieces are platelets. So this is your figure that shows the different activity that occurs. So here we have a myeloid stem cell. If you have an erythrocyte colony forming unit stimulating it, you're going to go through erythropoiesis. If you have a megakaryocyte colony-forming unit, you're going to go through thrombopoiesis. If you have, there's a lot of different colony-forming units here, so for all the different white blood cells. Or you can go down the lymphoid stem line. Lymphoid stem line produces your B and T lymphocytes as well as your natural killer cells.
Hemopoiesis is the process of blood cell formation, which occurs primarily in the red bone marrow. Hemopoiesis starts with undifferentiated cells called hemocytoblasts. These stem cells give rise to the many different cell types that make up the cellular elements of blood. A number of hormones and growth factors, known as colony-stimulating factors, or CSFs, influence hemocytoblasts to differentiate along either the myeloid or the lymphoid cell line. The myeloid cell line forms erythrocytes, or red blood cells, and megakaryocytes, which give rise to platelets. Myeloid stem cells also form leukocytes, or white blood cells, except for lymphocytes, which are produced by the lymphoid cell line. Hemopoiesis along the myeloid cell line follows one of three pathways: erythropoiesis, thrombopoiesis, or leukopoiesis. Erythropoiesis produces red blood cells. It begins with stimulation of myeloid stem cells by CSFs. This produces a progenitor cell that gives rise to a proerythroblast, the first committed cell along this pathway. The hormone erythropoietin initiates the erythroblast stage, during which proerythroblasts are stimulated to form erythroblasts. The erythroblast begins to synthesize hemoglobin and gradually decreases in size, giving rise to a neuroblast. At this point, the nucleus is ejected from the neuroblast, resulting in a reticulocyte. After the reticulocyte enters the bloodstream, its organelles degenerate, at which point it is considered a mature erythrocyte. Thrombopoiesis produces platelets. Like erythropoiesis, it also begins with a myeloid stem cell that produces a progenitor cell when stimulated by growth factors. The progenitor cell becomes a committed cell called a megakaryoblast. In response to the hormone thrombopoietin, the megakaryoblast differentiates into a large cell called a megakaryocyte. Platelets are formed when thousands of small cell membrane-bound portions of the cytoplasm break away from the parent cell. These isolated fragments enter the circulation as platelets. Leukopoiesis, the formation of white blood cells, involves maturation of three different cell types. The myeloid cell line gives rise to granulocytes, eosinophils, basophils, and neutrophils, and monocytes. The lymphoid cell line produces lymphocytes. Granulocytes and monocytes share a common stem cell. In granulocyte maturation, the stem cell is stimulated by CSFs to produce a myeloblast, which then gives rise to promyelocytes. These cells form the three myelocyte subtypes. Eosinophilic myelocytes differentiate into eosinophils. Basophilic myelocytes differentiate into basophils. Finally, neutrophilic myelocytes develop into neutrophils. The common granulocyte stem cell also participates in the formation of monocytes. This stem cell will give rise to a monoblast that differentiates further into a promonocyte and then a monocyte. The lymphoid stem cell is also involved in leukopoiesis, which results in lymphocyte formation. This stem cell differentiates into B lymphoblasts and T lymphoblasts. These mature into B and T lymphocytes, respectively.
All right. We're going to stop here, and in my next lecture, we'll talk about erythrocytes, okay? Have a wonderful day or evening. Bye.